did. I was supposed to give a talk on secret sharing over networks, but then I was very inspired by Professor Tilatar's talk. But I was not I'm not Tilata, right? So I couldn't just remove it. I just kept it and a few slides at the end so that if someone just comes at me with, why did you remove it? I can still show them something. So I thought, so there was a lot of, we heard a lot of talks about distributed storage, in particular regarding locality, local repair of codes. And Tamu gave a wonderful talk this morning. And then Professor Vijay Kumar gave a talk. During the lightning talk, Sergei Yekhanin put forward quite a few questions. But so I will give a student's view of the thing. Right? So I will be able to tell you something that has almost zero overlap with what all of them said. And they basically cover all of distributed storage. So I don't know how am I going to do that. Just to give you a reminder from the lightning talk, what I talked about is you have a graph right over here, and then you can store one bit in any of the vertices of the graph, and with a repair condition that if anyone is unavailable, you can just go to the neighbors to reconstruct that. So I asked that how many bits of information can be stored in this graph with this constant. So these are the recovery set, right? So for one, you can go to all of them. It's not like anything is small or big. So you're given this graph, right? So as I said, there are many talks on this repair locality topic, and then there were many on gap to capacity. And I was just going back and forth between these two topics. And so this talk is going to might be a bit haphazard, so I want to put a disclaimer. Don't be offended if you see your result in a way that is not understandable. Hopefully by the end we will have enough apologies to everyone. Right. So, and if I say that some bound is easy or some bound is hard, it doesn't mean that your bound is easy or your bound is hard. Yeah, so we start from this. Like in 2011 or maybe 2010, I looked at this bound. So you have a code which has three parameters, n, k, d, right? So this is something we all know. This is the length. This is the dimension. No matter whether it is linear or nonlinear, we can think of this as dimension. It's log of the size of the code. And we have some minimum distance. On top of it, you are putting a new parameter, which is locality. I mean this set of authors. And they are saying that what is this R? It is if you lose any symbol of a code word, you can look at most R other symbol to recover that. And then this nkdr must satisfy this bound right over here. Now this bound looks very much like a singleton bound. So what I thought when I saw this for the first time, it looks pretty easy, right? And if you just go through the proof, it's not really difficult to prove, and you are not losing a lot. I mean, be it nonlinear, linear, and someone asked this morning that whether you can get a counterpart of this bound for binary or not. And you can get it. It's not that difficult. We will come to that, why it is not that difficult. So it really doesn't matter. But what then I thought is these codes are very much like LDPC codes. Right. So here is again the definition of locality. So you have this code word symbols right over here. And if anyone is lost, you can just go to some other set of symbols to repair it. Right. So if you just look at the symbols of the code words, then for each symbol you have a repair group. So the uncertainty in that symbol, given this small repair group, that must be equal to 0. So this is exactly similar to LDPC codes, right? So is there any difference? Like, are these codes? So LDPC codes might be a overkill, because in LDPC codes you have small local repair group. You have much more than that. You have, what would be a good sanity check to see that these codes are not really LDPC codes? Right. So one way that I thought at that time was just look at the random error channel or random erasure channel, which no one really looks at in case of storage. So if you have an erasure channel and you want to see the gap to capacity, then our locally repairable code closing that gap any more than what LDPC codes can do, right? So we know that any LDPC code is a locally repairable code. But so are they as restrictive as LDPC codes in terms of reaching the capacity? So that is the kind of question I want to ask. And for erasure channel, it's not very difficult to answer. And not only binary erasure channel, any other erasure channel. And that will give us some more insight into this locality problem. And so what really happens? So here is a simple proof of the gap to capacity of locally repairable code, how far away they are. So if we go back to this bound, you see that if you are, in terms of rate, if you are epsilon away from the singleton bound, your locality grows as 1 over epsilon, order of 1 over epsilon. That actually follows from this one. And that happens for the case of binary and so on. So let's look at the capacity now. So to look at capacity, we look at the entropy at the output of the channel. So suppose I is the set of coordinates that are erased by BEC. It can be a QAD erasure channel as well. Now we just look at the entropy at the output of the channel. And this is pretty standard that from Fano's inequality, we know that if the average output entropy of the channel is, if the rate is strictly greater than that, then your probability of error is bounded away from 0. But here, we can consider this. So this is kind of a standard thing that you can do for LDPC codes as well. So then what you can look at this output entropy as a random variable, as a function of the channel, right? So the channel is introducing random erasures. So you can, and what we are going to show that this locality will make this random variable concentrate to some point. Right, which is not exactly at capacity, but a little bit far from the capacity. Right, so right, so far so good. So we have, so then we have to do a little bit trick. So if you have a locally repairable code and you just shuffle the coordinates of the locally repairable code, it remains a locally repairable code. Right. Now suppose T is the number of coordinates. So for each symbol of the locally repairable code, you have a set of a recovery group. Right? So suppose T is the set of coordinates such that the number of the recovery group actually appears before it. So if you have a linear ordering of symbols, then you are assuming that. Now, an ordering must exist. You can just take a random permutation and show that there exists an ordering of this symbol such that the size of T is always greater than n over r plus 1. Okay? Just do a random thing and average. Okay, so we are taking that ordering of coordinates of code, right? Now, we look at this subset of coordinates in T whose repair groups are completely unerased. We are computing this output entropy, and we are looking at the subsets of the coordinates whose repair group appear before it and completely unerased. So those bits are they are just redundant. So my output entropy must be the size of the unerased positions minus U, because U's repair group appear before it. It's completely repairable. So, but you know that how much can U be? This expectation of U has to be greater than or equal to 1 minus p to the power r, because all the r locations are unerased times t. Right? So you can. So if you take the expectation of this output entropy, it will be something like this. This is the average version of unerased coordinates minus this, right? But now we are done, because you know that this output entropy, this is a Lipschitz function. If your channel change a little bit, it doesn't change a lot. So not only this expected value is this, there is like huge concentration. It's concentrated around this value. You can just use the standard Martingale argument. That has been like the age exposure Martingale argument or anything for LDPC code. So you basically have this kind of result, that if your gap to capacity is epsilon, then local recoverability or locality is at least log of 1 over epsilon, exactly like LDPC code. So not only these codes are, any LDPC code is a locally repairable code, they have the same gap from capacity, right? Although the proof is a little bit different. Now I'm thinking that, okay, so they are very much like LDPC code, so I should go back to a graphical representation of these codes, right? And we just had a graphical representation drawn some time back. right over here. So it's not like really LDPC code, but some kind of graphical representation. Now here is what I am trying to achieve at this point. My thought is it's not coherent, but here is what I want to do. So in storage, I am doing this local repairs. And then if there is a catastrophic failure, I have this distance guarantee, but I still have to, like in Sak talk, if you have catastrophic failure, you have to go back to Reed-Solomon decoding. It's not that you just go on doing this local repairs and then globally correct something, even in a storage network, right? So if you have one failure, you can go to small number of other symbols and recover it. But then if you have 10 or 15 failure, you cannot just go on doing this local repair and correct everything. But in LDPC codes, you have that kind of property. The local decodings eventually converge, right? But this is a different code. So I'm thinking about a graphical representation, and this graph is nothing but this graph problem that I talked about, right? So you can think about this storage graph, again, coming back. And now these are your recovery set. So this graph is just like that. Now that I have arrived at this point, I can think of this graph as my storage topology. And I can think that that is given to us. So let's just formalize this problem. We'll just put some formula so that we know that this is well defined. Am I going too fast or too slow? Just stop me. OK. So I have, so I can define a storage code given a graph. What is that? So suppose in each vertex, I'm putting a random variable x1 up to xn. So I have a code. So this is a RDSS code. That means recoverable distributed storage system code. And then I have a set of deterministic recovery functions that actually maps from the set of neighbors to this vertices, so whatever is the content of the vertices. Right? And I can do a lot more things. I can actually relax the definition of recovery. I can have probabilistic recovery. I can do like all kind of relaxation. And it's wide open. Even the analysis that I show for gap to capacity, that works only for erasures. For errors, I don't know. It's much, much harder. And so it's wide open. And this is, so for any codeword, I must have this repair guarantee. And the capacity of this graph, we can call it the storage capacity of the graph, is the maximum log of maximum size of such codes. So this capacity is now given on this storage topology. And OK, I will give some more motivation as well. But this is not really an artificial problem. I then talked with people, and it seems like a pretty nice model. This is what I did in the case of Lightning. During Lightning talk, I said I motivated it by saying that giving some simple graph and show there is some graph if we have enough number of servers where the problem becomes non-trivial. For example, for the case of 2 servers, if I want to store such that it is recoverable from the other one, I have only 1 bit of storage. For the case of 3, I can have 2 bits of storage. And for the case of 4, 2 bits of storage means I have x, y, and x plus y over here. It has the repair condition that if any one gets destroyed, I can just go to the neighbors and recover it. I cannot store more than 2 even if I have 4 nodes and a topology like this. And here I can store 2.32193 bits because, yeah, if you are in the Lightning talk, it is pretty apparent how you do that. So the size of the code that I can store over here is 5. And this is exactly how you do this. So all these code words are valid if your recovery functions are this. And these are all nonlinear functions. So whenever we think of repair locality, we always think about some kind of parity check. But LDPC code may be not really linear, right? So you can make nonlinear LDPC type of code as well. And here is an example where with linear you can store only 2 bits, but with nonlinear you can actually gaining substantially. And this is not one example. You can actually construct hierarchy of example based on this, where you would be able to achieve this. And it's quite practical because to consider this kind of topology, because all servers are not connected to each other. If you look at cloud storage systems, even and some links between servers are easy to establish, some links are not. And then there you have to consider for physical proximity, architecture of different storage systems, the platforms, the connections. So it's probably a good idea to even consider a weighted graph, right? So when you are requesting a server which is far away, you can put a cost on that request, right? So that will generalize this problem. But before just going to that, we want to see whether we can solve the basic problem. Right, again, there is another angle then I saw that this problem is interesting from, and that is there is this quite popular problem of index coding that many people are working on. That's actually pretty close to this problem of storage capacity. And let me give you a brief overview of what is index coding problem. So in index coding problem, you have a set of n users. And each wants some information. So user 1 wants x1, user 2 wants x2, and so on. But they don't have it. What they have is a subset of side information about other users, what the other users want. So for example, and that gives you a side information graph. For example, here vertex 2, this guy wants x2, but he has x3 and x1. By the way, all this graph doesn't have to be undirected. They can be directed as well. All the problems, all the questions are well defined. So 2 wants x2, but it has x1 and x3, and so on for all of the vertices. Now there is some omniscient broadcaster who knows everything. Now, given this side information graph, how much information does he broadcast so that everyone gets what they want? That's the index coding problem. Okay. It was proposed in this paper first, and there are significant progress made in these other papers. Index coding is not the main topic, but so I'll not just go through it. Again, even for index coding, it has been shown that the linear capacity and nonlinear capacity are different. And so on. So do you see the connection? Is the correction very, very straightforward? It's actually, yes.
You mean the index coding?
Index coding and the storage capacity problem.
I think it's a nice observation. The only thing is you're looking at how much you can store.
Right.
In codes of locality, you're also looking for global distance in addition. Which
exactly. I'll come to, yes, that has not been captured here. Right. So the kind of the hope is that by doing this local checks or do something, we might end up having a large distance. I don't know that yet. For example, if the graph is such, if you are free to design the graph, for example, you can make it an expander or something like that, so that you do all this local check, but globally also you have a distance. Okay, but you can, given any graph, which might not be expanders, you might not have any control over this graph. Then you can put the constant of distance as well, and we will see how does things look like in that case. Right, I think, how long do I have? Actually, 5 minutes. Okay, good. Right, so this is actually, the index coding is the source coding version of the channel coding problem that we are talking about. And it can be shown that, okay, so they are actually a little bit of dual, linear or not. So in case of linear, if you have a linear storage code, you can actually look at the dual code of that linear code. It becomes an index code. That's actually pretty nice, but even for nonlinear, they're pretty close. So if you have an index code of length L, then you have a storage code of dimension n minus L. Because you actually look at all the set of vectors that are mapped to same index code, so the same message that the broadcaster sends, and that actually becomes a storage code. On the other side is true as well. It's with a little bit of gap, and you can prove it by doing some random translation. Because of the interest of time, I'll skip that. So index coding and this coding are quite close, and index coding it has received some attention. This is actually one of the hardest instances of network coding. It has been proved. So all the hardness results for network coding, they usually go through index coding. And for general network coding, only linear function capacities, even that is known to be NP hard. So index coding is pretty hard problem. But the storage capacity problem is not that hard. And that is not counterintuitive because here we are trying to approximate something which is n minus index coding, right? So even if index coding is hard to approximate, this might not be that hard, and that turns out to be the case. So I'll just tell you the case for undirected graph in the next 5 minutes. So what happens in the case of undirected graph, you can show that the storage capacity is always less than equal to the minimum vertex cover of the graph. And right, yeah, so that happens because you see, if you have an independent set in the graph, you cannot store any information in those vertices, because whatever information you put in there, they have to go outside of that set to recover it. The repair group must, because there is no edge inside that, right? So n minus whatever is the size of the independent set, you cannot store more information, more than that information. So you can basically go to n minus size of the maximum independent set, but that is exactly equal to minimum vertex cover. And also you can have a simple, so you can also store information by finding a matching in the graph. So you just find a matching in the graph, and then on each vertex, one vertex of the matching for each edge, you put 1 bit, you replicate that on the other side of the edge, right? And because of this simple relation between max matching and minimum vertex cover, you will always have a 2 approximation. Now you can also show that for general arbitrary graph, improving this 2 approximation is pretty hard, because then it will imply a better approximation, better than 2 approximation for minimum vertex cover, which is like dicey. It's, the unique game conjecture has to be not true for that to happen. For the case of undirected graph, this is significantly more involved, but you can still get a log type of approximation, and I can take questions regarding that offline. Right, and okay, so for directed graphs also you can do something. So I think I have, so whatever time I left, I will come to your question. So what we want is an extra minimum distance as well. Right, so I will say that if you want that condition, then you will have a bound like this. Okay, and this bound, if you see, okay, so how do you do this? So you consider an independent set such that the size of the neighborhood of this set is strictly less than k, so less than equal to k minus 1, say, right? Now you are just looking at the projection of the code restricted to this independent set and its neighborhood, right? Now that projection, because you have the size, as we said, the independent set, whatever information it has cannot be more than whatever it's, so well, because the independent set doesn't have any information, the entropy of this, the combined thing, it has to be less than k, or less than equal to k minus 1, right? Because it is less than equal to k minus 1, the entropy is strictly less than k, and the dimension of the code is k, the minimum distance has to be, because with minimum distance has to be n minus whatever is the combined size, right? And that actually gives me a bound on the minimum distance. So n is this, total number of vertices, minus the combined size of this u, the independent sets, and its neighborhood. And then I can try to maximize the size of the independent set, so its neighborhood has size less than equals to k minus 1. So this is my bound for the case of repairability with distance, where repairability is given by this graph. Now, if it were a regular graph, there exists, and you can show that there exists an independent set by Turan's theorem or something of size this. So you can just plug it in, and you get back the simple bound that we started with. Right, so that's why I said this bound is not that difficult to compute. There are other ways to compute it, of course. Right. So that's basically it. I should really thank my co-authors Venkat Chandar, Greg Vornel, Vivek Kadambe, Ankit Rawat, and Sriram Vishwanath. So I really skipped the entire literature of regenerative code. Maybe I can give a different point of view there as well, but that's for some other time. And those who were not cited during the talk but should really be cited, Dimakis and Karthik Shanmugam, they gave me some nice pointers. There is some work on complementary index code, which relates very much to the storage codes by Chaudhary, Langbar, and Springston. Tamo, Barg, and Papai Leopoldos are just being there. I have not in particular mentioned their work, but I have not spoken about it because their work speaks for themselves. And if you are interested in further in this topic, so I have something in archive posted last year. You can just search and find it. Thank you very much.
So time for maybe one or two quick questions.
Can you formulate the computation of the storage capacity as some kind of optimization problem? So how would it look like? You can get two approximations through this, but
that's very.
What's the kind of problem?
It's a very combinatorial problem. There is no nice formulation for, or I don't know any nice formulation. So even for the case of directed graph, I don't have a two approximation because there I don't have a notion of matching, right? I can basically go to cycles and try to do cycle packing. So, but these are all approximations. So direct this problem, it has some relation to Shannon capacity and stuff related. So I can only have upper and lower bound and then try to formulate those bounds nicely and have some answer. But not in particular, I don't have a linear program formulation, for example, for this problem. But I can have like upper bounds on this problem or lower bound on which I can, right? So that's the only approach that I have so far.
Is it clear? Maybe it's a silly question. Is it clear that if I increase the field size or the alphabet size, the capacity does not go bad and does not decrease?
The capacity actually converges to a limit that you can prove. So you can, instead of storing 1 bit, you can store a very long code, right? And then basically you can normalize by the length of the code. And that function you can show that it is super additive. And like so it's basically converges. So, but the rate of convergence I don't really know. I have not looked at that.
Thank you very much.